Okay, so in this video, we are going to try to understand intuitively the form of Schrödinger's equation for a free particle on a line. Okay, so remember what we have with a free particle on a line. So we have the particle is free to be anywhere on the real line, and it's described. Its state is described by a wave function, which might look like this. It's psi of x at time t. So this is maybe what it looks like at time t equal to 0 or at general time t, and we want to understand how this state evolves as t increases. Okay, so what we're going to do is we're going to assume, there's this one general principle. We're going to assume that the equation of motion is described by, it's a local differential equation, meaning it's this very important principle in physics, which is that of locality, that every point in space sort of minds its own business. Well, it minds its own business, but it sort of looks around at an infinitesimal neighborhood around it. So it minds its own business, but also the business of sort of a small neighborhood around itself. Okay, so now what do we want to say? Well, we want to say that the change in the state. So if you want to write d psi xt by dt, right? The way this is described is by the following kind of differential equation. The rate of change in the state at the point x. So if this was the point x, this is the time t, that's what the superposition looks like. And now what this point x does is it looks in its neighborhood, and it looks at a point sort of at x plus delta x and at x minus delta x. Right? So it looks in its tiny neighborhood, and it looks at its own amplitude. So this is what psi of x is, and it compares it to psi of x plus delta x and psi of x minus delta x. And it does this in a particularly simple way. So what it does is it looks at the average of psi of x plus delta x and psi of x minus delta x. So what's this average of these 2 points? Well, the average of these 2 points is that. Right? So what it's doing is it's comparing this point, which is psi of x minus delta x, plus psi of x plus delta x divided by 2, and it's comparing it to its own value, which is psi of x. And basically what this equation says is that if we look at this difference, the difference between these two quantities, so this value, so let's call this y, what Schrödinger's equation says is that the rate of change is proportional to y. So the rate of change of psi at this point x is proportional to the difference between psi at this point x minus the average of the neighbors, and the neighbors infinitesimally to the left and to the right. Okay, so now can you, as delta x tends to 0, can you describe what y is in terms of psi of x? So we can ask, can you describe y in terms of psi of x? Well, some of you might be guessing maybe y is just the, y is something like the derivative of psi of x. With respect to x. Well, that's a pretty good guess, but let's look at whether that's true. So suppose that that psi of x happened to look like a straight line in this region. So this is psi of x. There's x. Okay, and there's x plus delta x, x minus delta x. So what's the average of psi of x minus delta of x and psi of x plus delta of x? Well, the average of these 2 points is exactly that. And so y is exactly 0 because psi of x is exactly the average of psi of x minus delta x and psi of x plus delta x. So there's something else going on here. And so actually, if you think about it a little bit more, it turns out that y is proportional to the second derivative of psi of x with respect to x. Okay, the reason the way you might see this is that this difference, psi of x minus delta x plus psi of x plus delta x minus psi of x, sorry, this divided by 2 minus psi x, this is the same as psi of x plus delta x minus psi x I'm just putting this and this together, minus another psi x, and then I can subtract off psi of x minus delta x. Okay, so this first piece is proportional to the derivative of x, of psi x at x, and this and this is proportional to the derivative of psi x at x minus delta x. So when you subtract these two, it's proportional to the second derivative. And so what Schrödinger's equation says is that the rate of change of psi with respect to t is proportional to, so since I don't care about constants in this particular lecture, I'm just being very imprecise, I'll just say it's equal to the second derivative of psi with respect to x. Well, not quite. So you see, if this is all that was happening, then this would not be very good, because what Schrödinger's equation would say is that every point then tries to look like the average of its neighbors, and no matter where you start from, your wave function would eventually become completely flat. So to keep it from going flat, but still to keep the change proportional to this difference, what you do is move in the orthogonal direction in the complex plane. Okay, so let's see what this means. So remember our equation now is I d psi of x comma t by dt is d2 psi x comma t by dx squared. Okay, why I times this? So let's say we are working in the complex plane. This is real, this is imaginary, and let's say we have a complex number, which is like a vector in this complex plane. Okay, so now if you take this complex number and you instead, you could move it in some direction. So for example, you could change it, but if you change it in a direction which is I times itself, then you're changing it in like this, and what you're doing is you're basically rotating the complex number around, and it leaves its magnitude unchanged. And so this is the sort of thing that Schrödinger's equation is doing. It's saying, well, the rate of change is proportional to the second derivative, but we want to move it in the orthogonal direction in the complex plane, so that we actually keep the normalization of the wave function, so that it actually ends up still being a unit wave function. Okay, so let's step back and see what this has told us about Schrödinger's equation. So what it's telling us is, if you have a free particle on a line, okay, and there's some superposition that describes it, so it's some superposition that describes it. Now, what's happening to this superposition? Well, basically, every point looks around. It looks at its, every point x looks at its small neighborhood to the right, to the left, and it compares itself to its neighbors on the average of its neighbors on the left to the right. And it changes its amplitude at a rate which is proportional to the difference between itself and the average of its neighbors. Another way of saying it is, it changes its amplitude at a rate that depends upon the second derivative of the wave function with respect to x. Okay, so what it means is, so now think of at every point, the amplitude is not real, it's actually a complex number. So what you really have here at every point is a complex plane, and your amplitude is some complex number in this complex plane. So that's real, that's imaginary, and let's say the amplitude happened to be imaginary right now. But now what happens is the amplitude starts precessing, right? It acquires a phase. It starts rotating in this complex plane. But at what rate does it rotate? Well, it rotates at a rate which is proportional to the second derivative at this point. So at the points where the wave function changes very rapidly, the second derivative is large, well, it's going to rotate quickly. But where the second derivative is 0, it's just not going to rotate very much at all. And that's what Schrödinger's equation tells us about how the wave function changes in time. Okay, so now, as I said, in this form of the Schrödinger's equation, I've been very sloppy. I've just ignored constants, signs, etc. If you want to see what Schrödinger's equation for a free particle really looks like, well, it looks like this. It has a form I h bar, where h bar is the reduced Planck's constant. d psi by dt is minus h bar squared over 2m. M is the mass of the particle. d2 psi by dx squared. Okay, so we're going to look at this precise form of Schrödinger's equation in the next lecture. But for now, I just wanted to give you some intuitive feel about what it might be telling us about the evolution of the system.